Very good morning to all of you. I'm Mitu Galor. I'm working as assistant professor in St. Andrews Institute of Technology and Management, Gurgaon. I'm from Applied Science Department. Today, I'm taking my 11th lecture, and the topic of my lecture are meso compounds, absolute configuration, and isomers in the transitional metal compounds. So we have come to our topic is meso compound. Actually, meso compound is a topic which is related to our previous lecture, in which topic we have already discussed about the enantiomers, chirality, asymmetric carbon atom, diastereomers, optically active, plane polarized. So these topics are already discussed in our previous lecture. For meso compounds, I want to a short revision of this topic, just like the chiral compound. So chiral compound is the compound which have the carbon which have the all different groups attached to it. So this is the chiral compound. And for the meso compound, a meso compound is a molecule with multiple stereo centers. That means there are the two or more than two chiral center that is superimposable on its mirror image. The meso compounds are a chiral compound that has multiple center. They are optically inactive. So here we already discussed the chiral or the achiral compound. So as we know that the meso compounds are the achiral compound, and that has the multiple chiral center. So if the achiral compound is present, so they are optically inactive. We have already discussed the optically active and the optically inactive compounds. We know that when a compound, when a plane polarized light PPL is passed through the any compound, so if this compound is turns the direction of light towards the right hand side or towards the left hand side, so it is called this compound is called the optically active compound. And if the compound does not rotate the plane polarized light, so it is inactive, optically inactive compound. So it has an internal symmetry plane that divides the compound in half. Here we take the example of the tartaric acid. So the structure 1 is the tartaric acid and structure 2 is the mirror image of first structure. So here we can say that the structure 2 is the mirror image of the structure 1, or we can say that they are the enantiomers. Okay, they are the enantiomers. And here now the structure number 4, third, and structure number 4th, these are also called the enantiomers. So because as we know that the enantiomers have a mirror image relationship, so these are the mirror image, show the mirror image, and they are the optically active. But in this structure number 1 and 2 are the non-superimposable. We can see that structure 1 and 2, they are the non-superimposable. Okay, we can see here that these are non-superimposable mirror image, and so these are called the optically active enantiomers. I repeat again, structure number 1 and 2 are the non-superimposable mirror image, so these are called the optically active or enantiomers. And here we can see that the structure number 3rd and 4th, structure number 3rd and 4th are again they are superimposable mirror image. Okay, so these are again enantiomers. So, but when we see the structure number 3rd and 4th, as we see that structure number 3rd and 4th are not a chiral. Why? We can see here that they are not a chiral compound, because in this compound there is a presence of POS. Okay, so there is a presence of POS, so that these are not the chiral compound. Okay, so because the presence of plane of symmetry, here the is not the chiral compound. So these are optically inactive compound, or these optically inactive compound are called the mesoform. They form a mesoform. Okay, so we now we know the what are the meso compounds. So uh, now come to the next topic, which are the configuration or the absolute configuration. As we know that the configuration means it is the giving the numbering of our compound is the configuration. Uh, According to the CIP, these are the name of the scientist, which suggested a very similar procedure to simplify a particular configuration in terms of prefix. The prefix, these are the R and X, and R is taken from the rectus and S is from the sinister. So it is the system that is used for the naming of enantiomers or the diastereomers. We have already discussed the diastereomers. Diastereomers already discussed. Okay, diastereomers means they do not have the mirror image relationship. These are the diastereomers. So now uh, it is a system that is used for the naming of enantiomers and diastereomers. It is called the RS naming system. So here the some steps are involved. So we can explain the one by one. First step, firstly select the stereo center. Now it means the carbon with four different substituents. So here we can see there are the carbon are the four different substituents here. And in the second step, the sequence, we can select the sequence of the priority. It determined by the atomic number. So it means the higher atomic number is the higher priority. Okay. So in this example, we can see that there are the four different groups are attached to the carbon. So according to their priority, according to their atomic number, so we can give gives the number of this compound. Now third step, if there are the same atomic number, then what to do? Then going out one bond at a time. So here we can see the going out one bond at a time. Now come to the next step. In this step, if isotopes are here, so then the higher atomic weight is equal to higher priority. So here we can see again when the higher atomic weight, the higher priority is here. Then the position of lowest priority group, uh, listen carefully, the position of lowest priority group away from us as if we were looking along the C4 S bar. Okay, so according to the lower priority group, it is away from the us. Now, the other groups determine the direction of high to low priority. It is 1, 2, 3. So, if this is clockwise, if the center is R, it means right side. And if this is the anti-clockwise, so the center is the S is left. So here we can represent S and R structure. So this is the simple relative configuration. And now come to the absolute configuration. Actually, the absolute configuration means it is a fixed configuration, or we can say the actual configuration. So the Bisword in 1951 was able to determine the absolute configuration, or and we know that the this absolute configuration is using by the X-ray diffraction method. So it is also called the actual arrangement in the space of atoms or groups constituting a particular stereomers is called the absolute configuration. Here we take the some examples. Or it can say that that is the fixed configuration. Everywhere when we want to see or when we study this configuration, so that is called the absolute configuration. So absolute configuration of the some examples, there are the, first we take the glyceraldehyde. This one is the glyceraldehyde, and this next is the D is the D glyceraldehyde, or is the L glyceraldehyde. We cannot explain the which one is the D or which one is the L. yeah, how many amount of the D or how many amount of the we can estimate with the help of the laboratory. So now the second example is the lactic acid here. It is D-lactic acid and it is the L-lactic acid. And the third is the tartaric acid. So it is D or L of tartaric acid. So these are the subtopics which are related to our previous lecture of the enantiomers of the isomers. Firstly, we have discussed the meso compounds. I repeat again the meso compounds. It means meso compounds means if there are more than one chiral center, or we can say that is the asymmetric carbon atom is here, and if they can show the mirror image, but we can see if there are the POS is present here. POS is that is a plane of symmetry, and which can divide into divided a compound into two halves. So it is a POS. So when the POS is present here, so it means that compound is a optically inactive. And as we know that the optically inactive compound can't rotate the plane polarized light towards the right or towards the left hand side. Now, the configuration, that is the simply nomenclature of the organic compound. So how can we nomenclature? How can we give the number of the compound is the configuration, and then come to the absolute configuration. Absolute configuration is explained by the X-ray diffraction, X-ray method, X-ray diffraction method, or it is also called the absolute configuration, fixed configuration, which is present same everywhere. Now I come to the next topic, which is related to the isomerism in the transitional metal compound. It is very important, and before studying this topic, I want to discuss some important points. So here, these important types which are related to the coordination compounds or coordination chemistry. So here the first term is coordination entity. Coordination entity means the compound uh, constitute a central metal atom or ion bonded to a fixed number of ions or molecule. Okay, the coordination compound or coordination entity means that is the or we can say that the total number of the there is a coordination constituting the center metal atom or is bound with its um, ions or the molecules, or maybe it can be a ligand also. So the ligand is an ion or the molecule that binds to the central metal atom. So they form the coordination complex of coordination entity. So now the example, that is the FACN64. It is the coordination entity. Now come to the next point is ligand. Now discussing about the ligand. So what is ligand? So here ligand means uh, ligand is a ion or a molecule that binds to a central metal atom to form a coordination complex. Thus, maybe ions, small molecules, it may be large molecule or a small molecule, just like the ions, just like the Cl, Cn, NO2, SCN, etc. So donor atoms, these are also called the donor atoms. So these donor atoms, it may be monodentate, it may be bidentate, it may be polydentate. So in the monodentate, these are the examples of the monodentate here, just like the H2, it may be ion, it may be a neutral molecule also, H2O, Cn, and NO2, these are the monodentate. Again, to the bidentate, there are some examples of the bidentate, just like the ethylene diamine is the bidentate, or the auxiliate ion is also. Now the polydentate, there are two or more donor atoms of the ethylene diamine tetraacetate. So these are some examples of the ligands. Ligands means which is work as a donor, or is directly attached to the central metal atom. Here the formation of the chelator also. So now come to the coordination number. Next point is the coordination number. The total number of the ligands which are directly attached to the central metal atom is called coordination number, as we know the coordination number. Now the coordination sphere. So the coordination sphere is the when the central metal atom and the ligands that are directly attached to it and they enclose in a square bracket are collectively. So this is called the coordination sphere. So these are the important terms which is very necessary, which is very important before starting the coordination compound. So I repeat, the coordination entity, the coordination constituent of central metal atom or the ion bonded to a fixed number of ion molecule. That is coordination entity. Ligands, these are the ions or the molecules or the neutral compound where the central metal atom binds to the central metal atom to form a coordinate complex. Types of ligands are the monodentate, bidentate, polydentate. Now the coordination number, the total number of ligands which are directly attached to the central metal atom is coordination number. And the coordination sphere means that central metal and the ligands are directly attached to it, enclosed in the square bracket collectively. So that is called the coordination sphere. Now come to the topic, that is the isomers in the transition metal compounds. When we know the word the transition metals, the one word is what comes into our mind, that is the d block elements. So as we know that d block elements are defined as the element in which last electron enters in the d subcell of their penultimate shell, or it means the n minus 1, or that is the next to the outermost cell. It is called the transitional elements. And the coordination compound and complexes have the same chemical formula but different structural arrangement. And the coordination compounds, same molecular formula, but the arrangement of the groups are the different. So such compounds are the isomers, which have different the physical and the chemical properties. So there are the two types of the isomers. First, as the structural isomers, and another type of isomers is called the stereoisomers or the space isomers. So now, as usual, first of all, we come to the structural isomers. In the structural isomers, the definition is same as the previous lectures, that the same molecular formula, but the different structural arrangement of atom around the central metal atom, and it is mainly of the following types. So there are the 7 types of the structural isomers. First is the um, ionization isomerism. Second, the hydration isomerism. Third is the linkage isomerism. Then that is the coordinate isomerism. Then the coordinate position isomerism, and ligand isomerism, and the polymerization isomerism. So there are the 7 types of the isomers of the structural isomerism. So here we discuss the structural isomers of the transition metal firstly. So isomers which have the same molecular formula but the different structural arrangement. These are the structure isomers, and here these atoms are around with the central metal atom. So these are the structural isomers. Now as we know that there are the 7 types of the isomers. First, we have already know their name. The first type of isomers is called the ionization isomerism. In this this type of isomers is due to the exchange of anion. Here the exchange of anion between the complex ion and the ion outside it. Or we can say that this type of isomers occurs due to the exchange of groups between the complex ion and ions outside. So these are called the ionization isomers. So here the example of ionization isomers is this platinum ammonia hydroxide. So here in this isomers we can see in the first case, here are the NH3 4 OH2 and SO4 is from the out of the bracket. So, but in the second type of isomers, we can see that SO4 is exchanged with the OH. So it is called the ionization isomerism type. That means that the compound is differentially when dissolved in the water. So it behaves as a differentially when dissolved in water. This type of isomers is called the ionization isomers. Then come to the second type of isomers, which is hydration isomerism. And the hydration isomerism is here the hydration isomerism. Here, water is the most effective coordination agent. Therefore, the number of water molecules with any enter into the coordination sphere may vary, resulting in the formation of hydrate isomers. So here in the hydration isomerism, the isomers differ in the number of water molecules attached to the metal ion as the ligand. So here we can see the example. Here the example, and we can see here the number of the water molecules is 6, and in this type of example here the number of water molecules is 5 here in the bracket, and 1 is from the outside of the bracket, and here again the one molecule of water is there, and then the other the 2 molecules of water is there. So this type of isomers is called the hydration isomerism. Now come to the linkage isomerism. The isomers of this type occurs when more than a single atom in a ligand they may function as a donor. Such ligands are called the ambidentate ligands. Here the example of the linkage isomers. So it is the example of the nitritopentamine, where here the direct attached to the central metal atom ligands are the ammonia, and here is the ONO, sorry, ONO is here. So, but when we see the another isomers, so here nitrogen. In this case, in the first case, there is the oxygen is direct attached to the cobalt, but in the second, there the nitrogen is directly attached to the cobalt. So this type of isomers is called the linkage isomers. Now come to the coordination isomers. In the coordination isomerism, here this type of isomerism is possible when both the positive and the negative ions of a salt are complex ion. The two isomers differ in the distribution of ligands in the cation and the anion. We can see here the cobalt with the ammonia, the chromium and the cyanide, and the another type of ligand we can see the exchange of the ligand. It means here the chromium with the ammonia and the cobalt with the cyanide. So this type of isomerism is called the coordination isomerism. Now the next type of isomers is called the coordination position isomerism. In this type of isomer, this is due to the difference in the distribution of ligand in two coordination center. Here we can see that in the first case, there are the bromine is here, and in the second case, the propane is replaced by the Cl. So this is a, or we can say it is a polynuclear complex, and an interchange of ligand between two metal atoms give rise to another type of isomers, so called the coordination position isomerism. Now come to the next type of isomers, which is the ligand isomers. In this isomers, we can see that this isomers arise in those complex in which the two ligands are isomers themselves. And we can see that the two ligands are isomers. So here, as we can see that in the first case, the N-propyl amine. So here the CH3, CH2, CH2, and NH2. And now the second goes to the second structure. So we find it is converted into the isopropylamine. So these two structures are the ligand type of ligand isomers. Now come to the next type of isomers. This is called the polymerization isomers. Polymerization isomerism is actually, it is not a type of the isomerism, but in some cases we can study in this category. So this is not a true isomerism. since it occurs between the compound having the same empirical formula but the different molecular formula. As we can say in this structure, here the number of the chromium is 1, ammonia is 3, and CN is 3 in the first structure. And the second structure, there are the chromium is 2, and ammonia is 6, and the CN is also 6. So there is the relation, if we multiply the structure of one molecule with 2, so the empirical formula and molecular formula, the ratio is the 1:2. Okay, molecular formula is the 1:2. So this is the type of the all type of the uh, structure isomers as we have discussed in our lecture. I repeat again the types of the isomerism and the coordination compound. So here we have explain the types of the structural isomers in the transition metal atoms. So first type of the structural isomers is the ionization isomerism. Second is the hydration isomerism. Third is the linkage isomerism. Fourth is the coordination isomerism. Then fifth is the coordination position isomerism. Sixth is the ligand isomerism. Second type of the polymerization isomerism, which is not actually the isomers of the transition metal. So now I complete my lecture, and for any query you can discuss with me.